In a balanced multi-wire branch circuit, the current flowing through each ungrounded conductor, also known as the hot wire, is equal in magnitude and opposite in phase. In this scenario, the current through the neutral conductor is zero or negligible. Conversely, in an unbalanced multi-wire branch circuit, the current flowing through the ungrounded conductors is not equal or opposite in phase. This inequality results in a non-zero current flowing through the neutral conductor. To determine if a multi-wire branch circuit is balanced or unbalanced, you need to compare the currents flowing through the ungrounded conductors. If the currents are equal in magnitude and opposite in phase, the circuit is balanced. If the currents are not equal in magnitude or not opposite in phase, the circuit is unbalanced. Consider a balanced circuit example with two 120 volts loads connected to separate ungrounded conductors, with the neutral conductor carrying no current. The current flowing through each ungrounded conductor is 10 amps. Now, consider an unbalanced circuit example with two 120 volts loads connected to separate ungrounded conductors, but one load draws 15 amps and the other draws 5 amps. The neutral conductor carries 10 amps, which is the difference between the two hot wire currents. Unbalanced current can lead to several consequences. Firstly, neutral overload can occur, where excessive current through the neutral conductor can overload it and cause a safety hazard. Secondly, voltage imbalance can arise, where imbalanced currents can lead to voltage imbalances between the hot wires, which can affect the performance of electronic equipment. Thirdly, increased power losses can result, as unbalanced currents increase resistive losses in the neutral conductor, leading to higher energy consumption. Now let's delve deeper into the concepts of balanced and unbalanced multi-wire branch circuits. A multi-wire branch circuit is a type of electrical circuit that shares a common neutral conductor. It typically consists of two or more ungrounded conductors hot wires and a single grounded conductor neutral wire. These circuits are commonly used to provide both 120 volts and 240 volts power in residential and commercial buildings. Understanding the balance of current in these circuits is crucial for ensuring efficient and safe operation. In a perfectly balanced multi-wire branch circuit, the loads connected to each hot wire are identical. This means that each hot wire carries the same amount of current, but in opposite directions. Since the currents are equal and opposite, they cancel each other out in the neutral conductor, resulting in little to no current flow through the neutral wire. This is the ideal scenario, as it minimizes losses and reduces the risk of overloading the neutral conductor. However, in real-world applications, it is rare to achieve perfect balance. Loads are rarely identical, and appliances and equipment draw varying amounts of current depending on their operation. This leads to an unbalanced current condition, where the current flowing through each hot wire is different. In an unbalanced multi-wire branch circuit, the neutral conductor carries the difference between the currents flowing through the hot wires. For example, if one hot wire carries 15 amps and the other carries 5 amps, the neutral conductor will carry 10 amps. This neutral current can create several problems if it exceeds the capacity of the neutral conductor. Firstly, it can cause the neutral conductor to overheat, potentially leading to a fire hazard. Secondly, it can cause voltage drops on the hot wires, which can affect the performance of sensitive electronic equipment. Thirdly, it can increase energy consumption due to resistive losses in the neutral conductor. To avoid these problems, it is important to properly balance the loads on a multi-wire branch circuit. This can be achieved by distributing the loads evenly across the hot wires, ensuring that the current draw on each wire is as close as possible. In addition, it is important to use appropriately sized conductors for the circuit, including the neutral wire, to ensure that they can handle the expected current load. Another important consideration is the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect imbalances in current between the hot and neutral wires, which can indicate a ground fault. When a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are particularly important in areas where there is a risk of moisture, such as bathrooms and kitchens. In addition to balancing loads and using GFCIs, it is also important to regularly inspect multi-wire branch circuits for any signs of damage or wear. This includes checking for loose connections, frayed wires, and cracked insulation. Any damaged component should be replaced immediately to prevent electrical hazards. Furthermore, it is essential to understand the relevant electrical codes and regulations that govern the installation and maintenance of multi-wire branch circuits. These codes provide detailed requirements for conductor sizing, overcurrent protection, and grounding, among other things. Adhering to these codes is crucial for ensuring the safety and reliability of electrical systems. In summary, balanced multi-wire branch circuits are characterized by equal and opposite current flow in the hot wires, resulting in minimal current in the neutral conductor. Unbalanced circuits, on the other hand, have an equal current flow in the hot wires, leading to current in the neutral conductor. Understanding the difference between these two conditions is essential for ensuring the safe and efficient operation of electrical systems. By properly balancing loads, using appropriately sized conductors, installing GFCIs, and regularly inspecting circuits, it is possible to minimize the risks associated with unbalanced multi-wire branch circuits. To further illustrate the concepts of balanced and unbalanced multi-wire branch circuits, let's consider a few more examples. Imagine a multi-wire branch circuit powering two identical lighting fixtures, each drawing 5 amps. If both fixtures are connected to separate hot wires of the circuit, the current flowing through each hot wire will be 5 amps. Since the currents are equal and opposite, the neutral conductor will carry no current and the circuit will be balanced. Now imagine that one of the lighting fixtures is replaced with a larger fixture that draws 10 amps. In this case, the current flowing through one hot wire will be 5 amps, while the current flowing through the other hot wire will be 10 amps. The neutral conductor will now carry the difference between these currents, which is 5 amps. This indicates that the circuit is unbalanced. Another example might involve a multi-wire branch circuit powering a kitchen appliance and a small electronic device. The kitchen appliance, such as a toaster oven, may draw a significant amount of current, while the electronic device, such as a smartphone charger, may draw very little current. This difference in current draw will result in an unbalanced condition, with the neutral conductor carrying the difference between the appliance and the device. It is important to note that even small imbalances in current can have a cumulative effect over time. Over the course of a day, a week, or a year, the neutral conductor in an unbalanced circuit may carry a significant amount of current, leading to overheating and other problems. Therefore, it is important to address even minor imbalances as soon as they are detected. One way to improve the balance of a multi-wire branch circuit is to use a technique called load balancing. Load balancing involves strategically distributing the loads connected to the circuit so that the current drawn on each hot wire is as equal as possible. This may involve moving some loads from one hot wire to another, or adding new loads to a hot wire with a lower current draw. Another important consideration when working with multi-wire branch circuits is the potential for harmonics. Harmonics are distorted waveforms that can be generated by certain types of electronic equipment, such as computers, fluorescent lights, and variable frequency drives. These harmonics can cause additional current to flow in the neutral conductor, even in a circuit that is otherwise balanced. To mitigate the effects of harmonics, it may be necessary to use special filters or other devices to reduce the amount of harmonic current flowing in the circuit. In addition to the technical aspects of balanced and unbalanced multi-wire branch circuits, it is also important to consider the safety implications. An overloaded neutral conductor can pose a significant fire hazard, as the excess current can cause the conductor to overheat and ignite nearby materials. Therefore, it is crucial to take all necessary precautions to prevent neutral overload, including balancing loads, using appropriately sized conductors, and installing GFCIs. Furthermore, it is important to be aware of the signs of an overloaded neutral conductor, such as discoloration, melting insulation, or burning odor. If any of these signs are present, the circuit should be immediately de-energized and inspected by a qualified electrician. In conclusion, understanding the principles of balanced and unbalanced multi-wire branch circuits is essential for ensuring the safe and efficient operation of electrical systems. By following best practices for load balancing, conductor sizing, and overcurrent protection, it is possible to minimize the risks associated with unbalanced current and prevent electrical hazards. Remember, when working with electrical circuits, always prioritize safety and consult with a qualified electrician if you have any questions or concerns. The information presented here is intended for educational purposes only and should not be considered a substitute for professional advice. Always follow applicable electrical codes and regulations and take all necessary precautions to prevent electrical shock or fire. Remember to de-energize the circuit before working on it. Verify absence of voltage using a reliable meter. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. Inspect tools and equipment for damage before use. Do not work alone. Have someone nearby who can assist in case of an emergency. Be aware of your surroundings and potential hazards. Work in a well-lit and ventilated area. Take breaks to avoid fatigue. If you are not comfortable performing electrical work, hire a qualified electrician. Electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Also be aware of local and national electrical codes when performing any electrical work to ensure that it is up to code. Electrical codes and standards are essential for ensuring the safety and reliability of electrical systems. These codes provide detailed requirements for the design, installation, and maintenance of electrical systems, covering everything from conductor sizing and overcurrent protection to grounding and wiring methods. Adhering to these codes is crucial for preventing electrical hazards such as fires, shocks, and equipment damage. There are several different types of electrical codes and standards, including national codes such as the National Electrical Code, or NEC, and local codes, which may be adopted or modified by individual states, counties, or cities. The NEC is the most widely adopted electrical code in the United States, and it is updated every 3 years by the National Fire Protection Association, or NFPA. The NEC covers a wide range of electrical topics, including general wiring requirements, branch circuits and feeders, services, overcurrent protection, grounding, wiring methods, equipment, and special occupancies. It also includes specific requirements for different types of electrical systems, such as residential, commercial, and industrial systems. In addition to the NEC, there are also a number of other electrical standards that may be relevant to a particular project. These standards may cover specific types of equipment, such as transformers, motors, or generators, or they may address specific aspects of electrical safety, such as arc flash protection or surge protection. It is important to be familiar with all of the relevant electrical codes and standards before beginning any electrical work. This will help to ensure that the work is performed safely and in compliance with applicable regulations. Furthermore, it is important to stay up to date on the latest changes to electrical codes and standards, as these codes are constantly evolving to reflect new technologies and best practices. One of the most important aspects of electrical codes is the concept of overcurrent protection. Overcurrent protection is designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of electricity when the current exceeds a predetermined level. This helps to prevent overheating, fires, and equipment damage. The NEC specifies the required overcurrent protection for different types of circuits and equipment. The size of the overcurrent protection device is determined by the ampacity of the conductors and the rating of the equipment. It is important to select the correct overcurrent protection device to ensure that the circuit is properly protected. Another important aspect of electrical codes is grounding. Grounding is the process of connecting electrical equipment and circuits to the earth. Grounding helps to provide a safe path for fault current to flow back to the source, which can help to prevent electrical shock. The NEC specifies the required grounding methods for different types of electrical systems. Grounding conductors must be properly sized and installed to ensure that they can effectively carry fault current. In addition to overcurrent protection and grounding, electrical codes also address a wide range of other topics such as wiring methods, equipment installation, and special occupancies. Wiring methods refer to the way in which electrical conductors are installed and supported. The NEC specifies different wiring methods for different types of applications. Equipment installation requirements cover the proper installation of electrical equipment, such as transformers, motors, and generators. Special occupancies refer to locations with unique electrical requirements, such as hazardous locations, healthcare facilities, and data centers. In conclusion, electrical codes and standards are essential for ensuring the safety and reliability of electrical systems. By following these codes, it is possible to prevent electrical hazards and ensure that electrical work is performed safely and in compliance with applicable regulations. Always consult with a qualified electrician to ensure that your electrical work meets all applicable codes and standards.